Thank you. Hello, everyone. Can you hear me correctly?
Yes.
Cool. So sorry for the delay, for the technical issues. I'm Łukasz, as John mentioned. As John mentioned, I also work at Virtus Lab. I'm going to skip the positions. You can find me at Twitter. I dabble with functional programming and have been for a long time now. I'm also the lead of Scala SDK team for Pulumi at Virtus Lab. And today I'm going to talk to you about DevOps domain. Again, that's the third time I'm giving a talk in this domain at Lambda Days. I hope it's not the last. Anyway, let's quickly go through the agenda of the talk. So to have an understanding of how the properties might work in the domain of infra as code tools, we first need to understand how the infrastructure as code tools work in general. What is the programming model in them? Then we have to delve into the DSL of Pulumi tool itself, where there's a small change in what people might know as infra as code. Most of the time when we talk about infra as code, the tool that is used is the Terraform. Terraform doesn't allow you to use a real programming language unless you use some preprocessor that renders to Terraform. But Pulumi is different in this regard. Pulumi allows you to actually use a programming language and program the infrastructure layer. And then we're going to talk about the model of functional programming in Besom, which is the Scala SDK for Pulumi, and what interesting properties we might find there. I want to make a disclaimer. I'm not a mathematician. I'm actually a psychologist, a clinical psychologist. But it turned out that my way of life became programming, and I'm a programmer. So I wanted to give this talk to force myself to explore this topic deeply and to learn more about the implications of the category theoretical stuff for the domain of DevOps and infra as code. It is up to you to decide if I succeeded in learning how to name those things properly and to think about them with proper rigor. But for me, the most important bits are the guarantees that we obtain, because as long as they hold true in our software, the software we build on top of that is much more reliable, and this is what I personally care about. So to start, we will go through how those tools work. What is the main flow of an infra as code tool? And I'm going to shamelessly use Pulumi and Scala in those snippets here. But I believe it's not a very big problem to imagine the same content in Terraform's HCL. So we start with a description of what is the desired state of things as provided by the user, which is you. In this case, user declares that two resources should exist, resource 1 and resource 2. It doesn't really matter what those resources are. They could be network gateways, virtual machines, Kubernetes deployments, just resources. In the second step, the tool has to parse or run the declarations provided by the user and then compare them with what it knows about the infrastructure based on the persisted state. So the state is persisted at the end of the run. And if you haven't run the tool before, it will be empty, so everything will be created anew. If you did run it before, there will be a record of what has been created. So the tool has to compare what you want to create with what has been persisted. And in this case, we can already see that there's resource 1 that was created probably by an earlier run of the tool. Now, in the first step, the tool has to compute the plan necessary to bring the existing infrastructure to the desired state. In this case, it decides that the only thing necessary to do is to create the resource 2, as the first one is already present. In the last step, the tool executes the plan and applies the changes in the necessary order. So, key takeaways from this bird's view of what infra as code tools do. It's a stage evaluation model. The tool has to run a diff between the new evolution, so the new declarations of how the infrastructure should look like after the run, and what the tool knows about the infrastructure as it was before this run was executed. And then when the plan is created from this diff, the tool has to run CRUD actions, so create, read, update, delete, based on the plan to shape the infrastructure to match the declarations according to the plan that was computed. There are some nice properties that come out of this. Namely, it's fairly easy to see what the tool will do, because since we have the stored state, which is a snapshot of the previous run of the tool, and we have the new declarations, we can just compute the plan and just showcase that to the user. We can do dry runs and see what will be executed if user chooses to apply this plan. It's also fairly easy to do rollbacks, because in this case, it basically turns out that all you need is to just use a VCS like get, check out the previous commit, and run the tool again. Since it does diffs, it can just roll back to the previous state by diffing what has been, let's say, partially built, and then just reapply stuff that should have existed before. Okay, so let's talk about the actual hero of this talk. So Besom, which is the Scala SDK for Pulumi. First, a very quick primer on what Besom is. So Besom is a purely functional SDK for infra as code tool, Pulumi. It's written in Scala free. It can be used as a standalone infra as code layer. So you can just run it as Terraform from your command line. You can use it from GitHub Action, however you like, where it is just running your program that is applying some changes to your infrastructure. There is also another way to run Besom, which is where you embed it into another application and allow that application to control Besom programmatically. This allows you to do some novel use cases, like, for example, automated deployment of infrastructure for a new tenant. And this is exactly how Snowflake and CockroachDB use Pulumi. So when you create a new account or create a new bit of, new tenant in the parlance of those software as service. Yeah. When you create a new tenant, there has to be something that will create new databases, new compute nodes for you, and that's exactly what Pulumi does there. There's also a somewhat unique feature that only Besom has. As Besom was written with broad compatibility with Scala's bit fractured ecosystem in mind. So thanks to that, Besom works with two most prominent effect systems in Scala, which is Cats Effect and Zio. And now we can go and talk about the actual anatomy of the Pulumi DSL. So as seen in Besom. But most of those things are actually the same or slightly different between different SDKs of Pulumi. So Pulumi supports TypeScript, C#, Java, Go, and Python, besides Scala. So we have the most basic building block, which is input and output. Those are the two main channels through which information flows in any Pulumi program. The more concrete one of those two is the output. And the output is basically a wrapper over some kind of an asynchronous data type like promise or future. And this data type is present in all the SDKs, even in Go. Outputs are used everywhere where a value can be dynamic and can appear during the runtime. This means that it is used for use cases like configuration. It is, most prominently used for all the values that are loaded from the infrastructure. So when you create, let's say, a new S3 bucket, all the properties that AWS provides that are dynamic, that are only available during runtime, those values are provided in outputs. in this scenario, which is when those are properties of a resource, output also has an additional role. It's used to propagate the metadata of the resource that this output was a part of originally. Inputs are actually just aliases over row values and outputs, so that's a union type. And they are used for all the scenarios where you want to pass some information as part of the configuration for another resource. Now, a few words about resources and resource constructors. Resources are product types. They contain information about the created infrastructure, and everything inside of them is always wrapped in outputs. So that means that those informations can arrive dynamically. You can see a partial definition of a S3 bucket here. So it's in Scala parlance, it's just a case class with a bunch of fields that are outputs of something. Those values can also be products. They can contain other properties also wrapped in outputs. It's a foreshadowing. If you know your category theory, you already know what's going to happen. Then we have resource constructors, which are basically the apply functions of resources. They are kind of special. They perform the most important bit of work in Besom, which is the work of declaring the resources. They also return outputs, but those outputs contain those newly declared resources. The most important bits of information about resource constructors are that they are memoized and they're asynchronous. This will come up later. It's quite important for the overall mechanics of the DSL to remember those two facts. Now, resources that are to be constructed have to be configured somehow. You have to feed them the information about how you want things to look like. To pass that configuration, a special family of classes that end with an args suffix, bless you, exists. So those args classes are generated with all parameters being inputs. As you might recall, inputs are just type aliases for union type over a row value of A or input or output of A. So those classes allow you to put any information into the configuration of newly to be created resource. It can be a row value like plain string or just an integer, or it can be a value that is derived from another resource. This allows you to establish dependency relationships between resources and also allows Pulumi to track and infer the order of creation and deletion of stuff, because stuff that is dependent has to be created and deleted in correct order.
Yes.
Next, we have stacks. Stacks are okay. Let's talk object-oriented programming. If you speak object-oriented programming, how many of you do? Well, at least some. A stack is an instance for a class, where the class is the blueprint, the Pulumi program is a blueprint. If you run it, it creates a stack. Stack is a single instantiation of the blueprint that the program is. You can create multiple stacks out of the same program. And the common use case is to just create multiple environments from the same program. Once the blueprint is evaluated, a stack is created. And what is very important is that stacks can have export properties, which are basically very similar to the properties that we have on resources already. They are also outputs. And stacks can be referenced by other stacks. That means that stacks are composable. You can use Pulumi in a way where you have multiple stacks that reference each other, and you have multiple layers of your infrastructure. Now, stacks are, from the programming perspective, the return value of a Pulumi/Besom program. When you are writing a Pulumi program, the last thing that you're going to return from your Pulumi run function is a stack. Here's how this looks like when you return the stack from the program. It has two parameter lists. First, contains all the effects. It's a lazy runtime. All the effects that have to be evaluated that are dependencies of the stack. for the stack to exist, to contain all the resources that it should contain. And the second one, available as the exports method, is for properties that one wants to expose from the stack, so to make them available for use by other stacks. Now, the last bit, finally, we have components. Components are Pulumi's way to aggregate resources in logical bits that can be used and reused in different contexts. So you can easily imagine, for example, a Redis deployment for Kubernetes could be a component that contains multiple different Kubernetes resources that are necessary, like secrets, the deployments themselves, things that are necessary to set up Redis on Kubernetes. In this case, you have a bit of code where you have just a single input, the count of replicas, and you have a component of the type Besom example Redis, and then there are resources that belong to that. When you are using components, Pulumi shows you components as separate namespaces in the deployment plan, and the main, as I mentioned, use case for them is to facilitate code reuse and modularization of code, so you can share components. Excuse me. If you're part of the platform team, you can share components to other teams, and they will be able to have packaged bits of infrastructure to use with an easier interface without knowing all the details inside. Okay, so now let's get to the meat. Functional programming model in Besom. As I mentioned before, runtime is lazy, so it's just like in Haskell's I/O, or if you're familiar with Scala, it's just like in Cat's Effect I/O or Zio. If you don't use a value, if it's never referenced by anything else, it's a dead code. It doesn't do anything. It won't be evaluated by anything. Now I know that many of you, if you are familiar with Cats or Haskell, are familiar with type classes and how those abstractions work, but we don't actually use abstractions in Besom. It is possible to define them. We could have instances for type classes from Cats and Cat's Effect, but we chose not to do that because actually hiding the DSL would be, it could lead to some nasty surprises. We'll talk about what those surprises might be in a moment, but basically when you're working with infrastructure, the infrastructure concern is the most important thing in the program you're writing. And if you want to use anything effectful from the world of Cat's Effect or Zio, for example, you can do that because we'll get there in a moment. It is possible to lift values from other effects into effects of the DSL. But well, still we have a lot of useful properties, even if we don't have type classes. So let's talk about output. Output, as I mentioned, is the core building block that we use to push all the information, to transform data in a Besom program. And I know there's no type class, so it's a functor, it's an approximation, but there is a map function defined, so it is a functor. And you can use it in any context. There's also pure, so you can create a new output containing a new value that you need. You can use zip, which is in Scala's parlance closest approximation to app, which is the function available for applicative functors. We don't actually expose app. It is available lower in the runtime if we haven't deleted that. But we do have zip, and we do what is the most common operation available on applicative functors in Scala cats, for example, which is zipping and exposing that as a tuple of two things. And we also have an error channel. The computation can fail. You can use output error method to create a failed computation. So there's a set of things, set of properties that we have already based on that. When I say that, those things actually pass the Lowes checks. from discipline in cats. The question is, actually, because as I mentioned before, we have a foreshadowing. We have constructions where we have products that have fields that are also products, and those products are wrapped in outputs and have fields that are also wrapped in outputs. So this kind of necessitates that we have the power of monad available for the output. But this actually is a very interesting topic because it's a very good question whether we actually need that. So in this small snippet, we have two resources being created, and you can see that the second one uses a property called sidebucket.id as part of the args. So there is a direct dependency between those two resources. And Pulumi will figure that out. It will create them in the correct order. You can see that they are at the same nesting level. They are defined as vals in the same scope. Now, what happens if we run this? We can see that everything looks fine. They are at the same nesting level in the plan for Pulumi deployment. But what happens if we actually use a flat map? This is where things get a bit weird, because what happens now, we are using a property, bucket domain name, which is a dynamic output. It's something that gets computed during the runtime, and it's available only in runtime. Now, given this fact, if we flat map on this output and create a resource inside of the scope of this flat map, what happens is that the declaration of our resource is no longer in the, let's say, global scope of the Pulumi.run function. It's now in the scope of the flat map function, which is only executed when this output has a value, which is runtime only. So that means that due to the fact that output is also a monad, it introduces a complication. I like to call it superpower, but I have to admit that I'm still in the search for actual place where I would need this superpower. But the complication is that since we need to have the ability to see what are the changes going to be, if we use flat map and we chain those creations of resources, once we hit a dynamic output in our chain of flat maps, our deployment plan no longer mirrors the reality of what's going to happen when we apply that. It becomes dynamic. So it's, in this case, the bucket public access block is missing from the plan. So it's something that we would like to avoid, or at least inform the user about this capability. There is a way to think about output without the flat map capability, and I believe we could probably get around this by just leaving it as an applicative. But we wanted to have the same set of features that other Pulumi SDKs have, because they also allow you to do flat map on outputs. There is a new development in this scope that's available only in Scala, actually. Martin Luderski is going to talk about that tomorrow, and that's capture calculus. So it's a new capability being cooked in a Scala compiler that could allow us to track where we have precisely scenarios where other resources or outputs of other resources are used and they are being flat mapped, and then a new resource is created in that scope. We probably could use that, we could leverage that to find those places statically and warn the user, okay, you're doing something that is going to work a bit weird. Okay, so Now, a bit more gnarly stuff. Output A is actually free-like monad, and it's interpreted in terms of an underlying effect system. We can interpret outputs to Katz effect, to Scala's future, and to Zio. There's actually another level of interaction involved in how this is implemented, because there's the result A data type that DSL is a wrapper over. But given that all the operations on output strictly delegate to result, and that result is interpreted in terms of the effect system, I decided to cut it out, just for brevity. Now, for each supported effect system, there exists a natural transformation that allows us to transform the output of A into F of A, where F is the runtime that is being used to interpret this Pulumi program. Runtimes are provided as inputs, so when you're writing a Pulumi program and a Besom program, you decide upfront which runtime you want to use, and it's actually available in your global scope by the import of, let's say, besom.cats. Asterisk. You get the runtime there. Now, there's also another interesting bit, which is that in category theoretical speak, output also supports reflecting into the F type provided by runtime within the flat map. That enables computation expressed directly in the effect system that is underlying to be seamlessly lifted into the output context. I hope that makes sense. And then there's the most clever bit of the slide, which is that this actually mirrors the classic conjunction of free to forget, where the free is the left adjunct of the forget. The output here plays the role of the left adjoint, where it is used to construct computations. And then each runtime of some F, of some effect, is the corresponding right adjoint. It is used to interpret that computation. Okay, so we could also add here that Besom programs are invariant in terms of effect morphism. Clever people told me to tell that. That means that running the same program with another runtime and interpreting it to a different effect system yields no semantic changes to the deployment plan, or generalizing this thought to the infrastructure blueprint that the program encodes. You can switch the runtime and the semantics stay exactly the same. Now, we should also remember in the recap part that the monadic nature of output poses some difficulties given that, well, the DSL roles is to generate those deployment plans. So if we abuse the power that monad gives us, that we can have dynamic subtrees of computations, it's going to turn on us. Okay, so now the properties of resource constructors. I mentioned before that they are memoized. Is that the correct pronunciation of this word? Memoized? Yeah. Memoized, okay, cool. Thank you. So this is probably a bit confusing for people that are familiar with pure functional programming, but it makes sense in the scope of this domain. When you look at this piece of code, you would usually expect that this piece of code would lead to two evaluations of the S3 bucket output of this monad. Since it's a lazy effect, it should be evaluated 2 times. And in Katz effect, for example, that would yield the effect twice. This is not what happens here, because Pulumi and, well, the domain of DevOps, it demands that we declare resources only once, or rather that the declaration of resource is idempotent. We only put this resource in the plan to deploy once, And if we do this multiple times, it shouldn't have any other, side effects, basically. So in this case, we pass x and y values to the stack. Stack will evaluate at the end of the program, at the end of the world, it will evaluate all those effects. And it will hit the resource constructor for S3 bucket twice. But the logic nested inside of the resource constructors states that the effect itself is memoized, and it's memoized using the type of the resource, its position in the deployment tree, and the name of the resource. Names are unique, so it kind of boils down to a unique cache key. Okay. Now, another interesting property that Pulumi has. I mentioned before that resource constructors are executed asynchronously. What it means? Well, it means that when you actually create a resource using a resource constructor, the output is returned that contains the resource itself immediately. Now, the work for the registration of this resource with the Pulumi engine is happening in the background. It's actually executed on a separate fiber, so to say, happening on a different thread. And what you get is actually somewhat comparable to a promise. You get an output that returns immediately that contains a product type, a case class, that has fields that are also outputs, and those outputs will be fulfilled only when we get an answer from Pulumi. That means that all the dependency computations are also happening in the background. So if you declare a program that looks like this, and then you pass both those resources to the stack, those two resources, they will be evaluated in parallel. Now, that means that independent resource declarations are commutative. We don't really, we discourage the use of bind and flat map in Besom programs because of the aforementioned issues, the problems that you can have with dynamic subtrees disappearing from the deployment plans. But if you do this, the properties still hold. You can change the order, it doesn't impact anything. So from the perspective of the final infrastructure blueprint, those two things are commutative. You can see that it doesn't really matter if you do this flat map or if you just set them in a different order as values and then pass them in different order to stack. If they are independent, doesn't matter. Still, they are going to be executed in parallel automatically for you. Here's a small visualization of how this looks like. So if we have two resources, they're independent, there are no dependent properties passed between them. They're just going to be deployed in parallel, and you don't have to wait for them sequentially. Now, the story is different when we have those dependencies between those resources. If we have resources that are dependent on another resource, the order, like when you have this side bucket ID property being used here, then Pulumi infers the correct order and runs those effects in a correct sequence. Okay, last bit. Let's talk about Yaga. Yaga is our research project that delves into the area that we feel will be the future of large-scale system development. The core premise is that trivially invalid application deployments should not be possible at all, and that it's possible to fail-proof them using the information about what applications need to boot to start and what they expose. So valid configurations are things that applications need to boot. Interfaces, they depend on by means of consumption. Let's say we have an API that we need to consume for the application to work. Those are things that we need to start. And let's say our application is a gRPC server or OpenAPI server. So we have interfaces that other applications can consume. Those are things that we can extract as metadata from applications and then use that information to actually generate stuff for the Besom infrastructure layer and use that information to make something that builds on all those guarantees, all those functional programming properties that make software reliable, to build complete systems that are guaranteed to work if they compile. So, as I mentioned, Yaga's core functionality is that it does this bit of extracting this type metadata from applications, and it does that during artifact building process. So this is actually quite important. We do this at the artifact building process step because usually when you have an artifact, it's just published somewhere, it has a version, it's a snapshot of some application form that you want to use. You usually want to deploy a built artifact. When we extract this metadata from this process of creation of the artifact, we can then use this information to build matching code that is injected into your infrastructure build. This code is compiled. It's Scala. And most of that happens without you really lifting your fingers because Yaga is integrated with a build tool. At the current time, this build tool is SBT, but we have plans to support other build tools too. And this integration allows Yaga to track changes to the interfaces between your applications. So if you change, let's say, the shape of incoming requests in some API that you expose in one application that is also being used by another application, Yaga is able to automatically track the dependencies. It will know that, okay, this application uses that application. There's a client that is necessary to use that, and it's now out of sync. And you will get a compile time error. So current status of the project is that we have a POC that is working with AWS Lambdas. We are currently working on a full integration with microservices that will allow you to expose and consume OpenAPI interfaces, talk with databases, maybe in the future add gRPC, things like that. And this integration will, in the initial phase, it will support deployments to Kubernetes. So you will get a full component resource that describes the deployment of application. You can fine-tune that. You can provide a lot of configuration for small moving bits that are necessary for that. But you get that as a cohesive bit of infrastructure that is type checked, that matches exactly what is underneath in the application layer, and guarantees this way that your deployment will succeed. If you provide correct configuration that matches the types, it will just work. Here's a quick visualization of how this process looks like. We have an app layer, which is usually in most tools like Terraform. The Terraform has no idea what the application demands, what it needs, and what it exposes. In this case, Yaga serves as the glue code between those layers. And you can see that during the creation of the jar, the code generator will create the resource for the infra layer. You can then use that resource in your infra.scala file. And when you run the Pulumi app step, it will manage the deployment for you, and it will make sure that everything lines up correctly. Okay, so let's quickly talk about the properties of Yaga. Are we out of time already? No?
It's time to move to Yaga, yeah.
Okay, cool. Okay, so this part is a bit speculative. I don't really have a deep insight into what properties we're going to have, and I would gladly hear your ideas about the properties that we might find in this bit, because this is a novel approach where you are going to have the ability to embed your applications in infra layer as functions, basically. Let's talk about that. So Well, the most obvious things are that Yaga being built upon Besom benefits from all the properties that this runtime already has. So if you have independent Yaga resources, they are commutative. It doesn't matter in what order you declare them. Dependency tracking organizes the correct order of the deployment. If you have independent Yaga resources, they are deployed in parallel. You don't have to do anything to do that. You get all that stuff for free. Now, there are some new things that Yaga brings to the table. The first thing is that if you squint a little bit, if you think about that, Yaga turns applications into functions on the infrastructure level. Well, they need configuration. You have to provide a configuration as argument, but what you get as a return is the output of a resource. That resource describes all the properties that are, let's say, interfaces that this application has. If you have an application that is an HTTP server, you will get that server inside of that resource. It allows you to make those arrows between resources type safe and explicit. If you don't use them or use them in a incorrect way, compiler will complain. Now, the second interesting property is that Yaga's coding is deterministic. So the same source code will always generate the same infra code, and the same infra code will always yield the same infrastructure. Okay, so we have to finish. I think we're on time, hopefully. I would like to hear from you what other properties you think we could have, especially the ones that would be useful, but the theoretic ones would also be nice to hear about. Thank you very much. Here are the links if you want to take a quick picture.
Okay, let's thank Łukasz.